try and put on my broadcast voice because this is going to be, kind of on YouTube. Let's see how it goes. Going live. All right. Welcome back. We are INFR2350 in the winter 2021 semester, and it's week 1, part 1 of our broadcast, and this is our course intro. Right now, I'm on Zoom, and I'm broadcasting actually an image of me, as well as my PowerPoint in front of me as well. I'm going to stop the image of me, and I'm going to transport that image onto YouTube through our trusty tools with OBS. I'm using OBS. I'm kind of layering my image on top of everything else. So this is where you can watch it. You can watch it on YouTube. You can watch it live on, using Zoom. Great thing about Zoom is you can ask me some questions. We can interact. YouTube, you can do the same thing with live chat, but it's not the exact same. So that's why I kind of give you different options for you to participate, and that's part of it. Okay. So who the heck am I anyway? I'm not your regular professor. I'm not Dr. Alvaro, and I'm not Dr. Hogue, who is awesome. I'm Tom, right? And I'm a recent graduate of Ontario Tech University as well, just like I've gone through the same program as you. But I've been teaching. This is the funny thing about me. I'm an older guy. I've been teaching, technology in different languages since 2011. So I'm a polyglot programmer, which means that I can program in a lot of different languages: C#, C++, Java, JavaScript, Python, all kinds of different languages. And I take on a lot of different kinds of work throughout the semester. So what ends up happening is it doesn't matter whether I'm programming a game, let's say in Unity or on C++ with SDL or OpenGL. I take on whatever kind of contract I can get. I'm also teaching at other institutions, so you'll see me up on live broadcasting regularly. If you subscribe to my channel, I'll be broadcasting for Durham, for Centennial, for George Brown, for a bunch of other places. And why is that? Because I'm a busy guy. So right now, one of the things we've done over the last couple of years, we made my team and I, my GDW group, made an asymmetrical multiplayer VR game called Manos Returns. We took it to Level Up when it was actually a thing in Toronto before COVID hit us. So that's something we did. We also won the Level Up competition in 2018 for Best Overall Game. And that was really awesome. So it's still, Jonathan. So lots of fun there. So pretty happy about that kind of stuff. So I was lucky enough to kind of work alongside some great guys, in GDW. I had the luck to kind of combine with some great people. And now I'm doing my master's in VR security interactions. And I'm actually, Dr. Alvaro is my supervisor. And I'm using machine learning as well as VR and security interactions to figure out what's the best security interaction in VR. So that's kind of where my area of research is right now. Okay, so that's what I'm doing. So lots of fun. So that's a little bit about me. But let's move on. This isn't about me. This is all about you, this course. And this is what I offer to you. So one thing to note is this course is really packed. And if you've heard stories, I say that there's probably a few courses that are the course to pass that particular year. And this is one of those courses that is difficult typically for people to do well in. And not because I want to be difficult or anything else. Hell, it was difficult for me when Dr. Hogue was teaching me a few years ago. And let me explain why. It's not because the material is out of this world difficult or the math is super crazy. It's not about that. Typically what it is there's a lot of stuff coming at you in this course, and it's nonstop. That's why it's difficult. It's difficult because the math is there too. You have to worry about the math. You have to worry about all kinds of stuff. And if you're not good at programming already, then doing graphics programming is a specialized skill. So remember, when you're in game production, you're in the game industry, and you want to be a programmer, or you want to be an artist, or you want to be a 3D programmer, or whatever, right? Or AI programmer, or physics programmer, you can see that there's different specializations. So CG, computer graphics, is a very specialized field, and you have to think about things in a different way. Now, here are some assumptions I'm going to make for this semester. I'm going to assume that you know the basics of graphics. If you're fantastic at graphics, then that's okay. That's great. I'm happy with that. But if you're not, don't worry, because I'm going to start very, very slowly. Or your first assignment is something that we're going to use to do a little bit of a review for you guys, right? To give you a chance to review the pipeline, the graphics pipeline that you've learned last year, right? Or last semester, I guess it would be, Intro to Graphics. And to review that pipeline, to take a look at your code and have a chance to use it again. So that's the first assignment. And so we're going to step into this really, really slowly. And so that's what I want to do. I want to make it so that most of you are very productive and successful. That's my goal. My goal is not to fail anybody. Okay, that's not my goal. Marks have never been the thing that's driven me when I've been teaching over the last 10 years. It's not something that I worry about so much. I worry more about your learning. I worry more about your honesty and your effort. So if you put an honest effort into doing what I've asked you to do for this semester, you're going to do well. Okay. However, if you put little effort into something, then there's nothing I can do for that. So you have to kind of put in your effort in order for you to understand what's happening, like any other course. I'm not telling you something that's new here. Okay. So this is the course outline. So if you notice, in the first week, there are 2 lectures, Lecture A and Lecture B. But up online, when you look at My Campus, you'll see that on My Campus, you only see a lecture that runs between 11 and 12:30. Why? Because Dr. Alvaro, when he was putting together this course, he recommended because he's the director of experiential learning here on Ontario Tech University. And what he was thinking is that we'll do one portion that's asynchronous. So I'll be doing a recording later on today or this week, where you'll have a chance to see kind of a little bit more about object-oriented programming concepts. I'll be talking about those kind of things in the second recording. So I'm going to kind of step you through. I'm also going to be talking about assignment 1 details and your GDW project details during that time. Will we be using Otter again? I'm not sure what Otter is, so I don't know what what is Otter. What are you talking about? I'm going to be using a couple tools that I like. For example, Shader Toy. We're going to be using that this semester. That's for sure. A code framework for graphics last semester. Weren't you guys using Goop from that was introduced by Sean? If I'm not wrong, it's the same. It's Sean's framework. Oh, Otter is Goop. Okay, great. Yeah. All right. Otter is the new Goop. All right. So if it's Otter, yeah, then you'll be using Otter. Yeah, if that's the one that you're using. I know that Sean was talking about he's created a framework. Unfortunately, Sean wasn't able to be here this semester, but we have a great TA, Nick, which is, if you don't know him, he's fantastic. He's very fair with his marking, and he's very knowledgeable, and graphics is his thing. So I think you have a great opportunity with Nick, to really do well in this course. And he's very clear about the stuff that he does, right? So, so bear with the whole process. SpriteLib, no, we don't want SpriteLib again. SpriteLib is sold. But anyways, yeah, we're going to be working with Nick, and Otter, I guess it would be now, instead of Goop, to produce our OpenGL kind of effects, graphics, and so on. And it'll be the assignment framework that I guess you'll be using. All right, so week 1, we're going to kind of do an orientation. I'm going to be talking about assignment 1 details and GDW project details later on today or this week. I'll be going into detail, and I'll post it up on Canvas. So please hunt for that later on. You'll see that come up in the week 1 module. I'll kind of put it up there for you. And so you'll see that it'll happen like that every single week. You'll have a live session with me for about an hour and a half, and then we'll switch into this asynchronous mode. Sometimes I'll go right after what I'm doing here. So I'll just continue with what I'm doing. And some of you who can stay on and watch live. And some of you may end up having to go to other classes because there might be something else that you're doing. Okay, so that's what's the plan for how we're going to deliver the course. Okay. We also have next week, we're going to talk about shaders and the whole shader pipeline. This semester, we're going to be using programmable shaders, and I think you've done a little bit of that in Intro to Graphics. And we're going to continue with that and we'll do some post-processing effects and all that kind of stuff throughout the semester. And I'll talk about kind of the outcomes, what I'm looking for in this PowerPoint. So again, second week, we're going to think about we're going to review the graphics pipeline a little bit, and we're going to be talking about shaders. Okay, and a lot of the stuff we're doing is with shaders this semester. And this is where notice where we have this thing that says ICE 1. That's in-class exercise 1. So every time we have an in-class exercise or anything else that I have you guys do, there'll be something that you need to do in class that week. So starting next week, not this week, there'll be something that you need to do in class. And typically with something like shaders, I may ask you to look at something with Shader Toy, or maybe with Visual Studio Code, with some extensions in Visual Studio Code that you can actually do kind of real-time OpenGLES shader, kind of effects, like in real time. All right, so I'll ask you to do something. We'll be using RenderDoc for sure to inspect, kind of the pipeline and see when there's any issues. That for sure is going to happen. That's going to happen more with Nick than with me. So I'm going to talk about the theory. Nick's going to handle the heavy lifting, if you will, and he's going to work with you on the tech, which is what he's specialized in. Okay, so then week 3, we're going to hit assignment 1 is due. Now, notice that, look, assignment 1 is released this week, and it's going to be due in a couple of weeks, and you're like, whoa, that's pretty soon, right? And the answer is, yeah, it is, but it'll be due at the end of the week. So you'll have like kind of 2 and a bit weeks to get it done. Assignment 2 is more challenging, and I'll cover all the things that you need to know for assignment 2 between weeks 3 and pretty much week 4. Okay, so that's what's going to happen. So assignment 2 is due 2 weeks afterwards, just like assignment 1. So you got a couple of assignments happening pretty quickly. And we'll talk about which one of those assignments are individual and group assignments. So assignment 1, let me talk about that one, is individual. This is something that you're going to have to do on your own. Okay, so you're going to come up and demonstrate your knowledge of OpenGL and the framework, your use of Otter, the framework that Sean has developed and that Nick will go over with you. Okay, that's what you're going to be doing, right? So you're going to make a window, context, you're going to draw some kind of OpenGL shapes and so on. I'm in GDW3 currently, so how is that portion of my grade work? You'll be considered a non-GDW student for this course. That's what's going to happen, Adam. I know you're in GDW3 and your group did great. But yeah, I'll treat you as a non-GDW student for this course because there won't be an aligned assignment for you. And you can combine with other non-GDW students in this course as well if you like for group assignments, or do them on your own. Okay, it's up to you. Let's continue. So yeah, so week 3, we're going to go talk more about lighting and shading. And then into week 4, we're going to be talking about full screen effects. You'll put together a full screen quad to do your post-processing. And then we'll release assignment 3. That'll take us right into the midterm. So midterm is going to be an open book practical take-home test. Okay, and that's how it should be. What's going to happen is you're going to get the test probably in the beginning of the week, Monday, Tuesday timeframe. And then you're going to have the entire week to complete the test. And what I mean by that is that it's going to be an open book test that lasts for the week. It's going to be a week-long little mini project, if you will, a mini assignment. I'm not going to make it that difficult. I'm going to assume that this test can be run in a 2-hour period. Okay, so it's not going to be something that I'm going to say, okay, well, they got the whole week. Well, then I'm going to slam them with a crazy amount of work because they got the whole week to do it. No. It's going to be geared for a couple hours because I know you got other things going on during that week as well. All right, so that's something that I'm going to be doing for you guys as we approach week 5. Okay. The way we've done our tutorials start next week. And what's going to happen with that is Nick is going to assist you with your midterm. So during the midterm test, Nick's classes happen on Fridays. So you get the test on Monday. You have any kind of issues, any kind of challenges, then you meet Nick on Friday. And as a group, you ask him questions. He can help you through it. And so that way you do fairly well on the midterm test. That's the idea behind it. Okay, so again, I'm not sure yet if I'm going to make the test due on Saturday to give you the extra day, or if it's going to do on Friday. All right, for now, it's usually between Monday and Friday that I make the test work. Okay, so that's how we've done it for engines last semester, and we'll do it for the third years, and we'll do the same thing for you. I think it really worked well. I've got some great feedback that it kind of took the pressure off, which is what I want to do with you guys. I don't want to make it so that your semester this course is kind of going to pin you and pressure you to feel terrible. That's not the idea here. The idea is that you take something great away from this course that you can add into your game, and so that you can really enhance your CV and get a great job in the industry. That's what I want to do for you guys. And I can only do it with your help, of course, right? So it can't just be me doing, you got to do with me. So family days going to hit February 15th as normal, and then we're into study break for a week. By the way, in my year, we didn't have study break for a week. We had it for 3 days, which was terrible. And especially when you have a 5% assignment that is going to take me 50 hours to complete, right? So it's pretty crazy. So there was no break. The second half of semester is a little busier, I have to be honest. And by the way, I don't know if you've noticed these checkpoints, checkpoint 1, checkpoint 2, checkpoint 3. These are GDW checkpoints. And the way we're going to run GDW checkpoints is they're worth something. Okay, so all the checkpoints that we do together there's some value for all the checkpoints. Okay, that's how it works. And so there's the first checkpoint that's aligned with your review night with Gavin, because I know you have Gavin this semester for GDW, and you've already started your game, right? So the game that you're making for GDW. And so we're aligning together. Gavin and I are aligning, just like I did with James last semester. So that way your GDW is kind of aligned. The review is aligned with mine. Well, is it based off GDW? No, but what I want to try and do, Alan, as much as I can, is not give you extra work. So if I get you guys to do an aligned assignment for me, then what's going to happen is it combines with something that you're doing in GDW. So I'm going to give you some requirements for your game. And the great thing about that is that it's going to push you guys to produce something that's better. That's what the idea is behind it, right? So you're going to have several requirements that I'm going to give you, and I'm going to outline all those requirements during my asynchronous session later today or tomorrow. Okay, that's what's going to happen. So that's what's happening with the checkpoints. So checkpoints we get together. For example, the first one is a couple weeks from now, where you kind of tell me what your game is about, that kind of stuff, and then I want to see what your progress is on your aligned assignments. Okay, and that's really what we're going to focus on with checkpoints. And I'll remind you about this next week. In fact, I'll give you a lot of reminders about stuff that's available and stuff that's due. Okay, so second half, like I said, second half, we see another checkpoint coming in just after the break. We'll talk about shadow mapping. And notice that shadow mapping lasts a couple of lectures, because shadow mapping is actually quite complex and challenging to do. And depth of field. So depth of field will be the asynchronous piece. Again, this is a post-processing effect that we're going to see. We're going to get into week 8, where we do deferred rendering. And I'll be honest, this is where things get more complex. With deferred rendering, what ends up happening is we send everything to an FBO, several FBOs, and we create something called a G buffer. And the G buffer is kind of an accumulation buffer, if you will, where we add several different FBOs together, one for depth, one for normals, one for lights, and so on. And we combine them all together to create a kind of a post-processed effect. So you see lights normally in forward rendering, which is where we're going to start with in the pipeline. You're going to see that there's going to be a limit to how many lights you have based on your GPU. Okay. But as we get through with deferred rendering, there's an advantage to deferred rendering, and there's some disadvantages too. And what deferred rendering allows us to do is add many, many lights to our scene, a lot of lights, right? And whether you're using something like Unity or Unreal, or if you're doing things from scratch with C++, deferred rendering has great advantages, right? The disadvantage of deferred rendering is sometimes its performance, and there's some problems with deferred rendering as well. There's no, I would say, magic bullet that has it's one solution that fits all. It's not like that. With graphics, as you'll see as we talk about things and we research different topics in this course, you'll see that there's a lot of different ways of doing the same thing. And when you meet with Dr. Hogue in advanced graphics later on, I believe in 4th year, you'll see that there's a ton of ways to do the same thing. And sometimes there'll be some really cool, innovative approaches with math and, other ways of doing things that will really blow you away. And the effects that you can accomplish, even with a mediocre graphics card. You don't need an RTX 3070. All right, so that is what checkpoints are. Notice that there's ICEs, like I said, in-class exercise. So there's an in-class exercise here for shadow mapping, and there's an in-class exercise here aligned with deferred rendering. I can't do in-class exercises, based on shader toy for deferred rendering so easily, right? It's just not possible. So one of the options that we have for in-class exercise is kind of a live demo where I give you a small something I want you to do to change something around, to experiment or play. And then there's going to be a blog option as well. The blog option for in-class exercise is going to be a very short. I'm not going to make you do super blogs like Dr. Hogue. I'm not going to get you to do that. However, I'm going to ask, there's going to be some requirements for the blog. I'm going to ask you to do a little bit of research on your own. The blog will be due in week. So I'll get you to do it by the end of the week, right? As an example, there'll be some small amount of writing, okay? And a little bit of math if you want. But I'm not going to make it so that it's like killer math that you can't possibly do or anything. I might even make you do some diagrams if you feel like it. But more or less what you're going to be doing is you're going to be exploring some area. For example, when I hit deferred rendering for that blog, I might ask you to look at some games that use deferred rendering as an example. Come up with some examples. Show me where do you see the deferred rendering? What's the effects that you're seeing here? Why is deferred rendering being used? So these kind of questions I'm going to be asking you throughout the semester. Again, I'm not going to make it worth very much, and we'll talk about the weighting of these in a second. So, but the example here is that you're exploring, all right? And the opportunity for you to explore in a non-technical space for a technical kind of topic is a good thing because it gets you guys to think about things and how you can possibly use some of those effects in your game or maybe in the future. Okay, so this is what the idea with the in-class exercises are. They're interactive. Same thing with water and particles. Now, there's some things we can do with water and particles with Shader Toy, so I may ask you to do something, kind of more interactive there, okay? And it might be, instead of Shader Toy, it might be Visual Studio Code with some additional extensions that you can use, graphic extensions that work great with Visual Studio Code, and like real time. And what they use is something called OpenGLES, which is kind of a variant of OpenGL that works on the web and on mobile phones. Okay, so we'll try some of those as well. So that's the in-class exercise as we go forward. And so as you can see, it gets more and more interesting, water and particles. And then as we get into week 11 and 12, 11 is special topics. There'll be some kind of special topic that we'll cover, whether it will be things, some kind of particle effects or something really cool. We'll talk about our special topics as we approach week 11. And then into week 12, and it could be part of week 11 as well, depending on how we go, you'll be presenting your GDW project live to me, all right, and to the class. So what you'll be doing is you'll show what you have for your GDW a couple of days before it's due for Gavin. Okay, so I understand how this works because I've gone through this process before. And what's probably going to happen is what you're going to show me as an example for your GDW project by the Wednesday is going to be vastly different than what I see that when I attend GamesCon on the Friday with you. It'll be something completely different, right? And why? Because you're going to crunch. That's what we normally do. It's unfortunate, but we do that kind of stuff. We crunch really hard to get our GDW work done when it's all due. So something that's going to happen is you're going to notice that there's going to be slight differences between what you hand me or give me and what I see when you hand it into Gavin. And I fully expect that. And that's true. No, I don't think I have either. And it's not just one day. Usually it's a couple of days. I had a very, I would say, challenging taskmaster for me in my group. My producer, Joss, he was very challenging, and he didn't let us sleep for a couple of days until we got it done. So, but we got it done, and it ended up being great afterwards. So that was the advantage. So be prepared for that as we approach the end of semester. There's going to be some sleepless nights, unfortunately. So that is really the schedule that we're going to be following for the semester. There's a lot of stuff to cover, guys, in this course, and that's what makes this course challenging to digest, because what ends up happening is there's so much you're going to have to take in. Okay. From a course evaluation perspective, notice that my in-class exercises are worth 10%, and if I've got 5 of them, then they're each worth 2% of your final grade. Okay. In-lab exercises are important too. So Nick will be actually giving you exercises that are for marks, so that it's not something that you're just not going to just attend Nick's courses and then, or Nick's tutorials, and they're not going to be worth anything. He's also probably going to have at least 5 exercises that are worth 2% each, and they're going to be tied into the assignment requirements that I give you. So if I give you an assignment requirement as an example for some kind of post-processing effect, something like color grading as an example, then Nick most likely will cover the color grading aspect as an example in his tutorial. Yeah, that's what's going to happen. So, and it'll be worth marks. You kind of get double marks, a little bit of mark from Nick and some marks for the assignment as well. All right, which is a really great thing. Okay, individual assignment 1. That's coming up. And I said it's kind of a review of the graphics pipeline. It'll be due week 3, and it's worth 5%. Notice that weeks or assignments 2 and 3 are in small groups, and they're worth 7.5% each. The first assignment that's a group assignment is a lighting assignment, where you'll be doing basic post-processing and color correction. In the third assignment, it'll be advanced post-processing. So we'll talk about Bloom, Sobel, shader, and so on, and a bunch of other things that you're going to be doing during that assignment. That's going to be due week 7. And then assignment 4 is deferred rendering. So that's going to be the hardest one. Typically, that is the clincher. And when I did assignment 4, it was my assignment 2 back in the day when Dr. Hogue did it. And setting up that G buffer, making it work properly and everything else, it took a little bit of doing, especially when I tried to do things like volumetric lighting and those kind of things. It was quite challenging to do, but it was really cool at the end. So that's worth 10%, and that'll be due week 11 for now. Your course project, your whole GDW project, which is worth 25% of your grade, is due week 12, so the last week of the semester. And that course project includes videos. In fact, one thing I want to talk about for each of your assignments is that you're going to have to produce videos for all of them. And what I mean by that is there's going to be a video requirement. So a couple things you need to do when you make your videos. If you make them on your own, for example, you're going to have your assignment number 1. And when you do your individual video, you're going to pull up something like OBS, and you're going to spend, let's say, 5 minutes very briefly talking about, first of all, showing me that your assignment works. That's what you're going to do. And then talking about your code, all right? And you're going to talk about your code in the best way you know how. I don't expect people who are not specialized in programming, to be math specialists or awesome at talking about code. Talk about what you know is what I'm talking about. Discuss how you did the effect that I've asked you to make, all right, as an example. How do you put the objects, example, in an individual assignment 1, how you rendered everything in the scene, how you did it, what part of the pipeline were you using, how did you access it, how did you do this, how did you do that? And that's what I'm going to be asking you, in this assignment. So each assignment is going to have a video component. The group assignment is also going to have a video component, and the video component for the group assignment is going to be both partners, let's say. And by the way, when I say small groups, it'll be groups of 2 to 3. Let me explain that. So GDW groups this semester, if I'm not wrong, are 6 max. Correct me, guys, because you guys know it better than I do. Is it 6? 5 to 6. So there might be groups of 2, or there might be groups of 3. So 2 or 3, right? So when you do your group assignment, I would accept either a group of 2 or a group of 3. Okay. If you have a GDW group, I would like you not to do this on your own for a couple of reasons. One, it's a lot of work. A lot of these group assignments is a chance for you to research, to do some testing and all that kind of stuff. Doing this on your own would be very challenging for you to do. If you're a non-GDW student and you need to find partners, as we approach assignment 2, I'm going to ask for you guys to group up for assignment 2, and I'll produce different group sets for assignment 2, 3, 4 to give you a chance to work with different people if you want. So for example, let's say you have a GDW team of 5 people and you group up, 2 people group up the first time, and there's another 3 people in the first assignment, and then you want to swap people around in your GW group because maybe you want to work with other people. That's okay. We'll switch it up in assignment 3 as an example. Okay. And if you're someone who's a non-GDW student, again, what I'd like you to try and do is see if you can combine with another student who's non-GDW. This is not a bad thing. I also will accept if a non-GDW student wants to combine with a group of GDW students for their group assignments. So let's say, for example, I'm accepting groups of up to 3, and you know somebody who's a GDW. There's a GDW group that you're not part of, but they have a group of 5, and you want to kind of do 2 groups of 3. So a non-GDW student can join a GDW team for this group assignment, and I'm totally fine with that. Okay. For the GDW course requirements, if you're a non-GDW student or you're a GDW student from another year, let's say as an example, I'm going to treat you like a non-GDW student. Again, there's a couple of options. One, come up with a simplified framework, right, that will satisfy the requirements. Combine with a GDW group, right, that currently exists, right? Let's say, for example, there's a GDW group of 5, again, and you want to combine with them to make a group for my course of 6. I'm okay with that. I would even accept a group of 7 in this case. Why? Because as long as you can show that you've done some work for the GDW requirements for the group, and you help them for their GDW stuff for year 2, I'm fine with it. Guys, I want to make it as easy for you guys to integrate and to work together as possible. In this ever disconnected world that we live in, I want to be able to do that for you guys. So it's not going to be something that you're going to be stressing over. That's not the exercise here at all. It's something that's going to help you learn graphics. That's what this is all about. Okay, and I want you to be able to contribute as best as you can. All right, with each other. All right, so that is the GW. The midterm is practical and individual. And again, you'll have a week to do it. It'll be focusing on the graphics pipeline, specifically with programmable shaders. It'll be due at the end of week 5. Okay. And then finally, your final exam will happen in exam week. Right now, it's planned that there's 2 portions to the final exam, a written portion and a practical portion. Both portions will be individual and they'll be week long. All right. Typically, what we have is 2 weeks for an exam period. And what I try and do is for the first week of the exam period, I ask for a slot for you to write your written portion, right? And then the second week, I'll give you a chance to write your practical piece, which is just another little demo of something that I'm asking you to do. Chances are for your practical portion of your final exam, I'm going to ask you to do something with deferred rendering, because that's what we've been talking about this entire time, right? In the second half of semester. One thing to note is that the final exam is not cumulative. I'm not going to sit there and go, I need you to remember everything you did in the first half of semester or anything like that. I want you to consider that once you've left midterm, I'm not going to test you again on those things in the final exam. I expect you guys to know them, right? But I'm not going to, ask you, questions in your written portion that has to do specifically with something that we covered in the first half of semester. I'm not going to do that. All right. So it's kind of like modular that way. All right, so that is your course evaluation. Let's get into the course description. So again, what you're learning this semester is intermediate computer graphics. You're going to be learning shaders, lighting, post-processing, deferred rendering, and all kinds of the stuff that we talked about before. You're going to be using mathematical tools. You're going to do some research with the blogs. And we're also going to look at some trends with computer graphics. And you can do more of that when you hit advanced graphics. So once you're with advanced graphics with Dr. Hogue, there's some great research opportunities there for you guys. And if you're someone who loves graphics programming, it's a great step if you take advanced graphics. And I think it's going to become a requirement for you, if I'm not wrong, in year 4 now. So that's coming up. Let's continue. So again, other learning outcomes are things like, I want you to be able to identify a modern GL pipeline. Like, what does that look like? You should be able to, to talk about it. If you're in an interview and with, let's say, Ubisoft, and someone's asking you about the graphics pipeline, whether you're a 3D programmer, a 3D artist, a technical artist, a producer, a story writer, or whatever you're going to do, you should be able to talk about at least the graphics pipeline with some degree of familiarity. All right, that's what I want you guys to do. You should be able to understand lighting calculations to some degree. All right. So I'm not looking for you guys to be experts in matrix multiplication or anything like that. You guys have passed through that already. I'm not going to make you pass through that that crucible again. Okay. So, but you should be able to understand how those lighting calculations work and how the graphics pipeline, how it affects the graphics pipeline. Okay. So creating full screen effects is definitely an output of this course. So things like full screen effects, post-processing effects, screen space, ambient occlusion, those kind of things are things that you should know how to do and how to create. What are the processes? What are the steps involved in creating a post-processing effect, a full screen effect? Okay. Again, I'm not going to read all this. Some of this is for you to read. How are we structuring the course? As I talked about earlier, we meet on Wednesdays between 11 and 12:30 synchronously. Lectures will be broadcast live on YouTube again, and I will post the second part of each lecture during the same week, asynchronously. And again, I'll include videos and assignment details and a bunch of other stuff, so it's important that you watch the second part of the lecture. There will be questions. My assumption is that you're watching the second part of the lecture, that I'm just not doing it for no reason. And that's why I'm including things like assignment details and those kind of things in there. So please watch those videos. They might be longer. They still might be an hour long or whatever. And it's okay because I'm going to annotate them for you. So you can just like look at the video description and click on the video link, and then it'll take you right where you need to go. As opposed to, you having to swim through the entire video to figure out what I'm talking about. Okay. So that's what I'm hoping to do for you. Labs again happen on Fridays between 11 and 2. How do we do the GDW course stuff? Just like normal courses, it's broken down like this. Usually I'll post it, Andrew, by the end of the week. Course project is worth 25% of your final grade. And 10% comes from the GDW instructor if you're enrolled in GDW. If you're not, and you've combined with another GDW team, then you're going to get peer feedback at the for each of your, especially at the end of your final presentation is going to get peer feedback. And that feedback is going to be for you as well as from other people in the course. Okay, so peer feedback is where you're going to get your 10%. Okay, so how you work with other people, basically. And this is how it's broken out. So 15% of the course requirements comes from us, and 10% comes from Gavin. So each checkpoint is worth something, like I said. And notice it's like, out of 15, 5 for the presentation, 5 for the demo, 5 for the GDW progress and plan. And what I'm looking at the end is, what does your final progress look like after this semester? How did you integrate the requirements that I gave you for your aligned assignments? All right. Your demo and your is worth 7% at the end, and your final report with a video is worth 3% of your final grade. Okay, so that's how it's all broken out in terms of your GDW project requirements. And that's also on your outline, which is posted on Canvas. All right, any questions about all that stuff that I just covered? That's all about me, about the course, about my expectations and so on. Guys, I'm super excited to be your professor this semester. I'm really looking forward to working with each of you. And why is your spirit dying? I think it's, I know it's a lot, but we're going to be fine. We're going to work together. And here's a question. Fardeen says, what if for a checkpoint you make little to no progress on the align component for this class because you're focusing on some other part of your game? Well, again, I want you to talk about it. I think part of it, the progress is not about, I'm not looking for a hard and fast progress. Maybe you've researched something or you've got real reasons why you're working on something, but I want to hear from you. I want to see what your progress says, what your plan is, right? So this is where we can combine things like the producer. What's the producer telling us? How are you managing your project? How are you going to integrate the things that I've asked you? You should know that, but let's say checkpoint one, right? At the a bare minimum. And I'll try and push you along towards, making some of that progress for the assignment. And some of the assignments that I've given you hopefully will help you with the progress on your aligned assignments as well. Okay. Okay, so let's continue with, anyone else have any questions or concerns? Will these be like PowerPoint presentations, just talk about it and show it? I have PowerPoints as a backdrop, I'll be honest with you, but the PowerPoints are literally there for me just to keep myself timed, so I know that I'm on track. I'm not going to read every single PowerPoint. I'm not going to do that. The PowerPoints are also there for you to study from. So if I've given you PowerPoints, are you talking about your presentations or my presentations? I'm not sure what you meant. If you're talking about your presentations, yeah, your presentation is going to be a little PowerPoint presentation that's going to have very few slides. It's going to be maximum 5 minutes that you're going to come up with. I'm not looking for a whole story about your entire game, except for maybe the first checkpoint. First checkpoint, give me an overview of what your game is about. Show me your team. I want to see your faces, so be prepared to show me your cameras. I'm probably going to use Discord, our Discord that we're using here, our group Discord, if you will. So we'll pop into that, kind of the lecture room there that we have on Discord. And then I'll ask you guys to go in there and show me your stuff. Okay. And I'll ask different groups to come up. And usually during our presentation period, our checkpoint, I might give you something to do as well, some kind of research or whatever. Ethan says slides are a saver because I find it hard to take notes and pay attention at the same time. Yeah, I agree. I think it's a lot. My computer doesn't have a camera. You can use your phone, and we can talk about that. So there's really one thing you can use. You can download something called Droidcam, which is free. And whether you have if you have a smartphone, Aaron, do you have a smartphone? Yeah. So if you have a smartphone, download Droidcam, and you can use that to broadcast during those periods where I need to see you. Okay. Again, it's going to be like 4 times. I'm not going to ask you to do it a lot. But the idea is that I'd be able to see who you are and meet you, because one of the biggest problems we have right now is that I can't see you guys. I can't see your faces. I don't know if you're happy or sad. I don't know if you're excited or not, right? So one thing what I want to do is at least get to know you with the checkpoints. And so that's the only time I'm going to require you to put your camera on. So be prepared for that eventuality, okay? All right. And then, of course, during exams, I'm not going to use Proctor Track or anything like that during exams. I'm not doing that. All right. Your expression is dying on the inside. Okay. I'm not sure what that means, but it's interesting. All right. Let's continue. So yeah, let's begin talking about graphics again. We've talked about a lot of other things, but not graphics. And we've got a lot of slides to go through. And I'm going to hit the highlights here. Before I let you, kind of do your own thing as well for today. So what's trending? Real-time ray tracing, of course, it's the big news, kind of thing. Ray tracing is something that is, if you think about a line, that's shooting out of the camera as an example, and there's like thousands of lines shooting out of the camera as an example to create things like shadows and all those kind of things. Same thing from lights, where you have a light source that's shooting a bunch of rays. And what happens is with ray tracing, it's a computationally expensive process. Back in the day, ray tracing was unheard of for any kind of games. And the reason for this is because it's super hard to pull that off on the CPU. The CPU would die. And so that's why we do it all GPU side. The GPUs back in the day, when we first did this kind of stuff, this did not support ray tracing. In fact, most GPUs still, if you have a graphics, or a gaming rig right now, and if it's a couple years old, there might be a chance you don't have a GPU that supports ray tracing. So it's still not that mainstream. It's there as an example, and I think more and more cards support it. But some of the older cards that are not RTX, they don't support it, as an example. And some of the AMD cards, again, they also support it as well. So if you're lucky enough to have a 2060, let's say example, or higher, then you can support real-time ray tracing. as an example, as well as what we talked about earlier today, which is Nvidia broadcast. So you can do some machine learning on your GPU. Okay, so that's what's really trending right now. And let me talk about also the elephant in, kind of our space right now, which is, yeah, DLSS. Jonathan, thank you so much. I was going to talk about DLSS and Cyberpunk 2077. Woohoo, right? Who's got Cyberpunk 2077? Who hates it? Who loves it? Has anyone played it at all? I'll tell you, I have. You finished it, Adam. That's awesome. So some people, it's got a lot of bad press, okay? And it's got a lot of bad press because of its glitchiness. A lot of it, in my opinion, is the AI. I think that's where probably the worst part of the game is, the AI itself. But the story is awesome. If you like, the story behind Cyberpunk 2077 and that whole genre, kind of the cyberpunk genre, the, Blade Runner genre, if you will, as an example, it's awesome from that perspective. The graphics, the way things are done, is amazing. All right, to be honest with you. But the biggest thing with it is DLSS. DLSS really works great with Cyberpunk 2077. Once I turn that on, holy crap, it is amazing looking, and it's a way cheaper way of using 4K textures on objects, or something that looks like 4K textures. That's been really, kind of they use this, technique, right? That's supported again by RTX cards, that really allows us to use machine learning to fill in the blanks in the texture, which is really a cool little thing to do. So real-time ray tracing and DLSS is definitely something that's trending. And even our games, some of the people that hate Cyberpunk 2077 because how bad it is and glitchy and janky some of the things are, there's some really great things in that game as well. I think, I think, and this is an aside, if Cyberpunk 2077 only came out for PC this year, and they waited 6 months to perfect it for PS5 and for PS4 and for Xbox and so on, and the consoles, I think it would have been a way better release. And that's okay. But the biggest problem with that is that we get a lot of pressure in the industry right now from publishers, from investors who want their money back, and 10 times their money back. A good example of that is any modern AAA game that's part of a franchise. And we can see that the franchises keep getting watered down slowly because the pressure that they get from publishers. And I think that's what really clobbered Cyberpunk 2077, right? So that's my take on it anyway. But anyways, going back to graphics, it has some great, amazing graphics. And maybe one day what I'll do is I'll try and live stream some of that stuff so you can see what it looks like from my card. Again, I'm not going to humble brag here. Okay, maybe I will. But my system is pretty good. I built it. I've got liquid cooling on my GPU, on my CPU. I've got an i9 10900K, which is kind of the latest version, 10th generation Intel processor. I'm an Intel guy, not an AMD guy. There's different camps on that too. As an example, again, I'm running an RTX 3070 card, like I mentioned before. I'm using an MSI Godlike motherboard, right? That's my rig setup. And I've got 64 gigs of RAM with the capability of going to 128 gigs, right? So yeah, it's a crazy system. And that's why I can run, I'm sorry, I'm not trying to make it so crazy, but the reason why I'm telling you this is because this is why I can run Cyberpunk 2077 and I don't feel it as much. Some of the glitches that we normally would feel, as an example, when we play the game on a console. Example, my son who's trying to play that on his PS5, and he was able to get a PS5 recently. It's just not working right. And when we compare the two, we put them side by side, it's just not the same thing at all. Okay, so again, I think it needed another pass. And take a look at some of those other games out there that went through that same process. For example, things like when we talked about things like No Man's Sky was another game that was kind of something that they promised the world and they delivered nothing in the first year in 2016 when it came out. But think about what happened over the last 5 years from 2016 to 2021. Now, No Man's Sky is a good game, right? In fact, it's one of my favorite games to play, right? And the reason why it's so good is because they continue to work on it. And I think that's what CD Projekt Red's going to do with Cyberpunk 2077. So that's my little take on that. So again, RTX is what we're talking about. And it gives us so many things, the capability that that the RTX gives us. There's a pile of stuff, and if you want to read more about it, there's a link here down in the PowerPoint. We have a lot of different effects that have come up, things like destruction lately, advances in lighting, umbra and scalability, things that you can see. And again, there's a lot of links here that Dr. Alvaro has shared with us here in the PowerPoint. Dynamic skin and microgeometry, things that have really, really improved. Again, although I have to tell you, whenever I see a skin on a character, I look at it and there's still an uncanny valley when I kind of look at a character. It still doesn't quite look right to me, but that's just me. Maybe you like 3D characters and how when they look super realistic. I think the more super realistic the 3D character looks nowadays, there's still something that's not quite right. And I think maybe it's subsurface scattering or something that's happening there under the skin that's just not realistic compared to what we look like today. It's getting better, and they continue to get better and better every single time. And if you talk to Gavin about that in your graphics class that you're doing with him, he'll talk about why it doesn't look so good, right? So take a look at that and talk to Gavin about that. It's pretty cool. GPU-based procedural terrains. Serious Sam is a good example of that. High zombie throughput. How do we do zombie throughputs? A lot of this stuff is happening on the GPU. We're using the GPU with compute shaders in order for us to create that, and also geometry shaders to do things like with things like particle systems and all those kind of things. GPU physics, absolutely, Jonathan, and a bunch of other stuff that's happening on the GPU side that's never happened before, right? So a lot of progression when it comes to using the GPU. And Nvidia and AMD both really are pushing it. They're really encouraging you to use the API as much as possible, right? So a lot of really cool things. Water rendering and water effects. You're seeing a lot more of that. Reflections. Things that we couldn't pull off before without dropping our frame rate really, really low. All the kind of same stuff that we see exactly with DLSS, where we have a very high quality looking game with a very, very small texture. Something like a 1K texture can be kind of expanded to look like 4K with DLSS or even higher. And the GPU doesn't stop there. We're not just using the GPU for gaming. We're using it for all kinds of stuff. Finance, data mining, data science, machine learning, and a bunch of other things that we're using GPUs for today. Because think about this. We have this multi-core processor we keep on talking about. Our multi-core processor, my Intel 10900K, as an example. Who cares, right? If I have 10 cores, it doesn't matter. The GPU has hundreds of cores, right, as an example, which is way better. And this is the kind of stuff that we want to use. We want to offload, to my discrete CPU. And you're going to see more and more in that. I think you're going to see in the future as machine architecture changes that we're going to have a pile more specialized hardware that we're going to see on our systems, on our gaming rigs, which is super exciting to me, right? Because that means it gives us a chance to really, have some great effects. We have a lot of room in our cabinets, right? Like, my Corsair case as an example, I've got lots of room in there, even with my crazy GPU, right? And when you build your own rig, there's a lot of room to add more things. We're talking about the next level of PCI interfaces for motherboards these days, right? And so we have the capability of these discrete hardware cards that can help us with physics, with machine learning, with graphics, and with a lot of other things. So we're going to see more and more of that, okay? Yeah, I can't wait for that to happen. A computer physics card would be awesome. Or even something that helps us with matrix calculations, anything like that. And we're seeing more and more of that happening, especially with Apple's rollout of their M1 card. It gives us an idea of their CPU. So all that kind of stuff, right? We're seeing more and more of that being talked about over the last several years. So take a look at NVIDIA DesignWorks. The links here, it talks about things like occlusion culling, but you can see that there's so many things that are kind of listed here. And I've got the link here up online. Here's DesignWorks. They talk about things like CPU-based rendering compared to GPU-based rendering, they're comparing this 10 to 30 times faster, how it's done, that it's super scalable. All these things come from the Nvidia site. And again, like I said, they encourage us to use their APIs, to make all this work, right? So that's Nvidia DesignWorks. Again, they have this evolution of different kinds of cards they use for different environments, right? That they offer. Has anyone had a chance to use a Quadro card, or has anyone even heard of a Quadro card, right? It was kind of our first ray tracing card, an RTX Quadro, actually. And now they've brought RTX to the mainstream on GeForce, RTX GeForce, which is kind of what I'm using, right? So at the end of the day, there's different kinds of cards, and they're used for different environments and for different reasons, okay? VoxelBased Simulation. This is a great video, and I encourage you guys, or I think it's a video, yeah, and I encourage you guys to take a look at it when you have a chance offline. It's really neat. I can't show you a video because I'm also broadcasting a video. The rules of YouTube are what they are. So we talked about this. We talked about the idea that, why GPUs? Because guess what? We have a couple cores, 2 to, let's say, 16 cores on an average CPU, right? And some of the ones, as an example, that they have out right now, there's also cards or CPUs with 64 cores. The Nvidia, AMD's CPUs have up to 64 cores with the Threadripper CPUs. They're really awesome. Are they great for gaming though? There's Intel's claim to fame is single CPU performance, right? So and it's funny that they're even with 128 cores in a game like Cyberpunk 2077, it doesn't matter. It's single CPU performance because of the overhead that's involved in using multiple cores. So it's great for graphics processing, as an example, if the game uses it. If the game doesn't use it, and most games don't use, as an example, multiple cores in the CPU, they use the GPU, then it's more GPU heavy, right? And that's why we use the GPU over the CPU. CPU is programmable, but the GPU has many, many more cores. I know it's slightly better, and this is where, and then Leo's saying, you know what, the 128 core EPYC is awesome, and it is, right? And you know what, if you're doing things like design, or if you're using it as a workstation or something like that, then yeah, definitely go with an AMD, kind of rig. If you're using, I think still there's something to gain by using something like an Intel processor. I think Intel has got the message, although they're lagging behind. Before they were the leaders, and I think now AMD is really, is pushing the envelope in terms of performance and price. They're much better optimized in terms of price than Intel is, especially for price per core. I think AMD's got that right. But where Intel shines, or so they claim, is that single CPU performance and their clock rate. Let's talk about graphics APIs a little bit. Which ones do we know? Well, we know OpenGL. That's the one that we're using, but there's a ton of them, right? There's a ton of different graphics APIs. One thing that people get confused is that OpenGL is a game engine. And people say that kind of stuff over and over again. Well, I'm using my game engine, it's OpenGL. No, OpenGL is the graphics API, application programming interface, and your game engine is using some kind of rendering subsystem in order for you to render something or to draw something. And then we're going to learn about that in engines. All right, so there's a lot of different low-level and high-level APIs. One of the most modern ones, and when we talked to AMD, when we were at a level up and different competitions over the years, AMD says that most people don't even use OpenGL anymore, right? For their graphics, they use Vulkan, right? So this is where, you still need to learn OpenGL. OpenGL is a great learning vehicle, and this is what we're doing in this course. But when you get to advanced graphics, you'll have a chance to learn Vulkan, with Dr. Hogue, which is awesome. It's a great opportunity for you guys to do that. So again, yeah, I know there's. I'm seeing something on the chat on YouTube. Matthew saying Intel single core performance is actually slower now. Intel can only win with heavy tuning of CPU core, unicore. I agree with that. especially now with the latest AMD CPUs, their Zen 3s for sure. They're awesome. Um, and and again, now this week with CES, Intel has revealed more stuff to combat that with their 11th generation and 12th generation CPUs. So it's always going to be a fight, Matthew. I know Matthew's watching online on YouTube. That's what's going to happen. There's always going to be a fight between Intel and AMD, and I think that's fantastic that there is that way. So Vulkan is way better performance, but holy cow, to render a triangle with Vulkan, man, it's like 800 lines of code, right? So that's what I was going to say. It's like 1,000 lines to get going. And this is a problem with Vulkan, right? And so what we want to do is we want to put together, we want to abstract that. We want to encapsulate those things a little bit so it's easier for us to do with Vulkan. And so again, you're going to see that as we go forward. I think it's going to get better. I think it's going to get easier. Vulkan is a very low level interface, right? There's a lot of similar things that you can do with Vulkan that you can do with OpenGL. For now, though, as a learning, when you're learning the graphics pipeline, OpenGL is easier to learn. All right, so that's why we're starting you with OpenGL. Eventually, though, I think going forward, if we're forward looking, I think OpenGL is going to be like DirectX for us, where we don't do as much DirectX as we do OpenGL. I have to talk about DirectX as well. DirectX is still a viable thing to learn. I think it's a great thing to learn if you can learn DirectX. Why? Because then you can produce things on the Xbox, right? With OpenGL, you have some limitations if you're gonna programming things from scratch, for something like a console like the Xbox. Whereas DirectX, there's a lot of I'll be honest with you, there's a lot of market for DirectX as well. All right, so take a look at that. If you guys are interested in CG in general, DirectX is something that you want to also not put out of the picture just yet. And Microsoft continues to improve that API as we go forward. So again, lots of different APIs. There's different flavors of OpenGL. There's OpenGL and OpenGL ES for mobile and for the web. Things like WebGL comes from, they use the OpenGL ES interface and kind of a different kind of GLSL programming language that we're going to see that they use. Yes, they use a proprietary API for sure. And so why are we using OpenGL? Again, we talked about it just now because of its speed, it's cross-platform, because we can use WebGL, because it's easy to learn. That's why we're using it, not because it's the best thing. There's a ton of OpenGL games that have come up over the last little while. Even Doom 2016 was written in OpenGL, and that's a pretty good game. It's not bad. Although I have to tell you that Doom Eternal should win, kind of game of the year if it hasn't already for Steam. It was also pretty awesome. So pretty cool stuff for that we see. Yes, absolutely. Also written in Vulkan, and this is a fantastic thing. So Doom, it didn't win game of the year. That sucks. Because I'll tell you right now, Doom Eternal plays like butter. If you guys actually play, if you like a first-person shooter or something like that, you can configure that thing to make it sing. It's not the smoothest thing when you first start off, but if you remap those keys, man, and if you try Doom Eternal, it's pretty awesome as a shooter. So, but anyways, going back to this OpenGL, lots of OpenGL games that have been made and continue to be made as late as 2016. But Vulkan is the way we're going. Notice what it says is most of the games use DirectX. It's true because why? Because the ability for us to make them for Windows and or Xbox consoles. And this is where the fight between Sony and Microsoft, we're going to see what's happening. I know that the PS5 has great IP, right? That's going to come out for the PS5 compared to Microsoft's launch. But now that Microsoft has bought Bethesda and how they've got their Game Pass set up, I think there might be a shift in the interest to develop for Microsoft platforms. And when that happens, as we move in, let's be honest, PC is still the most popular platform to develop for. DirectX works great, and it's very similar to, in many ways, OpenGL. So once you kind of understand how how these kind of things work, then and once you understand one graphics pipeline, it's easy for you to apply the same kind of knowledge to other graphics pipelines. And OpenGL and DirectX are examples of those. So again, as a review of the graphics pipeline that's here in play right now, remember how things work. We have a bunch of data. And if you ever talk to Dr. Hogue about it, and if he's lecturing about graphics, he laughs about it, but he talks about a buffer as just data. It's just data. It doesn't matter whether you see something. And shaders, if you think about them, are just one big, if we talk about shaders just for a second, they're one big mathematical equation, right? If you think about it, one massive mathematical equation that kind of goes through the entire pipeline, right? So if you think about shaders like that, and you can of course have multiple shaders to combine effects, to create a composite effect, right? That of whatever you're looking for. But it goes through the entire pipeline where we have some kind of a vertex array. We have a vertex shader that kind of breaks down our mesh and into different vertices, right? Our mesh then goes through like triangle assembly, and then into the rasterizer. And the rasterizer, one thing that Dr. Hogue always likes to say is the rasterizer is the superhero of the graphics pipeline because it chops stuff up. And he didn't use stuff, but I'm on YouTube and I can't use the words he used. So it chops stuff up. That's what he says all the time, right? And then it goes into the fragment shader. It creates little pixel fragments as an example, and finally it combines into a frame buffer object. And the frame buffer object is this thing that is going to be rendering on the screen where we get our full mesh happening. So this is the kind of the graphic pipeline at a very high level. And we're going to talk more and more about this as we go forward. So the graphics pipeline can give us great effects, and everything from how we render meshes on the screen, and everything that you're doing with Gavin this year and next year is something that you're going to see how the graphic pipeline is really the way that we're going to render everything. We're going to load a mesh, some kind of mesh loader, and whether it's through Otter or if you had a homegrown system. I'm not sure if did Sean allow you guys to use Otter for your GW projects? Did he give you guys permission to do that or not? Great. So that's fantastic. If you can use Otter for your GW project, and it's an ECS, if I'm not wrong, out of the box, then that's fantastic for you guys, because that's a great kind of jump off point for you guys using some really cool technology to render your meshes. All right, so graphics pipeline, we take 3D models. Again, how we take 3D models, we break them up into vertices, right? You learned in animation algorithms, if I'm not wrong, last semester with Samantha, I believe, and Atia, if I'm not wrong, how to do things like mesh skinning and those kind of things. So those kind of things that you learned with them, and I'm thinking you learned, if I'm not wrong, you used Otter or Goop or some version of the framework, if I'm not wrong, to do just that, to take a mesh and to morph it, to do morph targets as an example, or something else. And it's a fantastic way of doing stuff. So we use the graphics pipeline really for 3D, not just for lighting, but actually to show the mesh itself. And whether we work from something like some kind of a voxel painting program, and we reskin it, and we retopologize it, and we bring it into Blender as as a mesh, and we use normal maps or whatever. That whole pipeline is possible because of OpenGL and a Vulkan and the graphics pipeline. One thing about models, 3D models, and you've learned this with Gavin, I'm sure, is you've got your rig, your skeletal rig that you're going to be doing. You're going to rig up the model, and I'm not sure if you're doing it this semester or if you're doing it next year, but it's kind of really interesting the way that we're using things like inverse kinematics and all that kind of stuff to kind of morph or deform a mesh in order for you to create an effect, an animation, or something like that. So really, really cool. So again, yeah, IK for that you guys did. That's fantastic. So that's how 3D models work. And I'm sorry, I'm kind of jumping through the slides, but again, I'm just talking to them. I'm not going to read every single one. And a lot of this, we're kind of going to time out in about 5 minutes. There's a lot of stuff in here that is for your reference. Okay. Example, triangles. This is some review. You guys should know about how triangles are are composed and how triangles are rendered. And one of the tests that one of my friends always gives to somebody who they're hiring as a graphics programmer is, hey, take my graphics pipe, my little graphics example, and hey, draw a triangle for me. Can you draw a triangle? If you can't draw a triangle with OpenGL, well, then see you later. I don't want to see you as a programmer. And that's the basis of everything. If you can draw a triangle, then you can draw any mesh. That's the idea behind it, right? So triangles are the basis for everything that we do with OpenGL in the pipeline. All right, so I'm just going to skip through this, but it really talks here in these few slides about how triangles work and the differences between immediate mode and modern GL. All right, so that's what these slides talk about here. Again, these slides are for your reference when it comes to understanding how GL works, OpenGL compared to immediate mode compared to forward rendering, let's say in modern GL pipelines. And so here what we show is the matrix calculations when we want to move objects or translate them from one three-dimensional coordinate space to another. Remember that pixels for us, really, they're just color and position more than anything else. That's what a pixel is for us. And going back to what Dr. Hogue always says, it's just data, all right? So don't worry about, what a pixel is. We have exactly what it is, a color and a location on the screen space. And a lot of times what we want to do is translate between our screen space coordinates, to our to 3D coordinates. So what did that look like? Okay, so here's an example of before what was shown in the slides was immediate mode triangles, right? Obviously, we're moving away from immediate mode, and here's a triangle using shaders, all right? So again, we have a vertex shader. We go through shape assembly, the geometry shader. Maybe sometimes we use a geometry shader, sometimes we don't, right? For particles, absolutely, a geometry shader. If I'm going to do procedural rendering, geometry shader. Otherwise, I may not use a geometry shader. It's going to go through the pipeline, go through rasterization, fragment shader, and then into our FBO. Okay, so again, immediate mode is called legacy, and we're not going to be dealing with that. One of the things that we talk about in your GDW document, the requirements for your GDW, is that we're not going to be using legacy code. We're going to be using, my expectation is that you're going to be using modern GL, which is, it's not a big stretch because that's how you're being trained. Okay, so projection, and this is the stuff that I was talking about. You guys should know a little bit about this, and this is a lot of review for you. You should understand about the camera, about the near plane and the far plane, and clip space. The idea of clip space, anything that's outside of the camera's view is not being rendered, but still inside the world. So that's an important thing. Different kinds of projections, the difference between perspective projection and orthographic projection, and how it makes things appear. And what are the calculations for these two different states, right? It's just changing the way the lighting calculations work and the way the camera works for how it's going to render to the screen. So we're taking a shape, and what we're doing is we're actually modifying the position of the pixel on the screen from a 2D perspective. That's how we can change the projection type, and we'll talk about that as we go forward. So again, going back to immediate mode, there's a lot here about immediate mode I'm going to skip because it talks about the difference between immediate mode and modern GL. Okay, so a lot of these slides here are just, I would say, review slides for you guys to look at. Am I going to test you on them? That's what you're going to ask. Again, there's no textbook in this course. So a lot of the stuff here is basically a discussion about the math and about how we use immediate mode to render stuff and how we're moved from immediate mode into modern GL. And I know I'm timing out, guys. Bear with me for a couple more minutes, and then I'll let you guys go for the day, and then I'll produce my asynchronous video later. So that's what these slides talk about, the math behind how immediate mode clip space works and how we can grab something from 3D and bring it into a 2D scene or 2D space, our screen, and so on. And then what the terms are in the calculations, all right? So these are the terms, when it comes to, from us translating something from one position to another using matrices, okay? So again, I'm gonna skip through all this stuff. It's here for your review. we talk about pixels. Remember what pixels are? Picture elements is where the word pixel come from. That's what's here. That's what it's showing here. So pixel elements are pixels. They're made of color and they're made of position, like I said before. So just a little bit of repetition there. Okay, and of course, what textures are is our ability to map an image, a bitmap, onto a mesh. And what we're doing when we do texture mapping, or these, we use UV coordinates. And I want you to think about what UV coordinates are. They couldn't use X and Y coordinates because we know X and Y is confusing. If I said take a texture's X and Y and kind of wrap it on top of an object, right? As an example, it got confusing. So we started using different variable names. So we use U for X for the texture and V for Y. All right, that's how it is. U and V is kind of an X and Y coordinate. All right, so that's what I want you to think about. A UV mapping, we map we take the texture, we sample each of the images or the pixels on a texture, and we remap it onto the mesh. That's what UV mapping is. And you'll learn more about that with not just here, but with Gavin as well. All right. So again, textures can also cover more than just position. It covers the texture coordinates as well. This is a great example of a group of vertices that have the position, the color, and the texture coordinates as well. We can include all of those things inside of an array, right? As a mesh, as an example. And what kind of array, if you were going to kind of look at this thing as an example, and I'm just asking you guys to see how you guys are looking at this. When you see this, what are we looking at when you're looking at something that looks like this? If you're going to look at this without knowing what it is, what is this thing? It's a square. Yeah, it could be a square or a cube, right? That's what it would be. Definitely a squarish mesh. Why? Because we have 4 faces, square. It's not, if we had 2 more, it would be we could think about it as a cube. We'd have 6 faces, right? But we have only 4 positions, 4 vertices. These are 4 vertices. We need how many vertices to make a cube? If we have 4 vertices to make a square, how many verts do I need to make a cube with? 8, right? Because we're just extending that the square in 3 dimensions. So this definitely looks like a square or some kind of quad, right? As an example. We're remapping our texture. We mapped our texture coordinates to the positions and the colors. All right, so this is kind of really cool. And that's what UV mapping is. It's almost like you're taking a 3-dimensional cube and you're unwrapping it. That's what you're doing. And we can see ourselves mapping our texture on top of the mesh. And that's what we're doing. We're sampling our texture and we're taking those samples and we're remapping the colors that we see in the texture to the vertices on the mesh. All right, that's what we're doing. Okay, so that's UV mapping from a very high level. Okay, again, I'm trying to get through 80 slides in an hour and a half plus introductions and what the course is about. It's flashing through some of these ones. Sorry. So really, really cool. We have our texture, or our mesh, and we have our texture, and we're just going to map it on to something that looks like this. A lot of times, what we can do is we can fool the observer to make a mesh look much more complex by something called normal maps, right? And not just by sampling, but by actually doing something like this. So if we can see that we get a super complex voxel-based object, we create a normal map or a texture, a very high quality texture of that super complex object. And then what we do is we dumb that object down. We actually remove vertices and we retopologize that object. And we use the same high quality texture on a low poly object to get a great effect. And we can do this with normal mapping. Okay, so that's something that you're going to be asked to do this semester for sure. Okay, so that's something we're doing. And here's an example of a normal map and how that works. So it looks at kind of the dark areas and the light areas of a texture, and it creates normal. That's why it's called the normal maps. And to give the sense of depth that an actual mesh doesn't really have. So we can have a very low poly mesh, but the way the camera looks at it, we're fooling the camera and the lighting calculations, we're doing the lighting calculations as if it was a much more complex mesh. And so we can pull off a much nicer image, or a much nicer looking mesh with really nice looking textures with very low memory consumption. All right, that's what neural mapping allows us to do. Okay, so and more about mapping, and you can see that there's a difference between, here's an example of no normal map, normal mapping by itself, and then how the normal map is applied to the texture. And we'll do some examples of that in class, through Shader Toy. We'll take a look at that. And now you got to think about how this is done. Can I do in immediate mode, can I ever do normal mapping? And the answer is no, I cannot. It's very difficult for us to do normal mapping with immediate mode. And this is why we use things like, post-processing effects and using things like forward rendering in order for us to do things like normal mapping. And we use the whole new modern graphics pipeline to allow that kind of stuff to happen. Okay, I think I've covered most of what it's saying here. Displacement maps also is a different type of information. So it's another kind of texture, right? And what it's telling us is how we want to displace the vertices from the texture information that we sample from. Okay, so we're actually displacing vertices now, physically changing the shape or deforming the mesh through the texture information that we're getting from our sample. All right, so it's kind of really interesting there as well. All right, and I think we've covered most of it. Again, when we think about all these things, we use different tools to accomplish this job. And some of the most popular tools are Mudbox, ZBrush, and of course, Gavin loves 3D Coat. So those are the three that I can kind of pull off at the top of my head. Blender also does the same kind of voxel-based sculpting that you can do. But we use tools for this. And all this talk, the thing that we've been talking about this entire time, how it all works for us and how it's going to work for us this semester, and I want to kind of end with this idea in mind, is the programmable pipeline, the programmable shader pipeline. We're using shaders. Shaders are the center of what we're going to be doing from now until the end of semester. Okay, I know that was a bit of a rush, guys, and that I piled everything in near the end. But again, I think the slides a lot of times talk for themselves. There's a lot of information in there, and there's a lot of little links. And if you go through the slides, I think one great thing about these slides is they've got a lot of information in them embedded in there. Go through the slides if you have a chance when you do some reading, and take a look at some of those example videos and links. And there's some great information in the slides as well. Absolutely being recorded, Ryan. It's on YouTube right now, and it's being recorded live on YouTube. Okay, any questions or comments about this stuff that we're talking about today?
Yes, sir. This is a note taker. I have a question. So all this is available on YouTube as well through Canvas?
It's going to be on. It's on Canvas and it's on YouTube. Absolutely, it's right. It's live. It's live right now. We're live right now on YouTube.
And do you go over to the next asynchronous class after this? Because I have till 12:30 right now. It's about 10 minutes over. So is this what will happen every week or
every week?
12:30?
No, usually I finish around 12:30. I'm sorry I went over time, but typically I try and finish around 12:30.
Thank you. Thanks so much.
No problem. All right. Are there any other questions before we depart for the day? Guys, thank you so much for staying after class. There's no in-class activities this week. It starts next week, Adam. So thank you so much for coming out. I really appreciate your participation, guys. I'm going to stop recording now, and I'll see you guys all next week. Thanks so much. Please take a look at the asynchronous portion, because I'm going to detail your assignment 1 details and your GDW details. So please make sure you look at that. I'll send you a notification as well. Thank you so much. Take care.